And the walls. The walls are just the, let's say, plexiglass walls on either side. And the segment, of course, is that part here rotating. If you go to materials, here, you see that there are 3 materials. Perfectly the same as before. If you go here, you see, he even get down to 5 megapascal. He did that because he was sure that will work. We put 20 here, it's also okay. So it's basically the same as before. But now a little bit to how a DM simulation, I said it's an explicit one, works in principle. We have the simulation now, and already started it a little. Let's proceed a little bit with simulation. So we simulate, particles are falling down. We'll see instantly what's happening. So you see the system during the simulation. You see the time here. Mine is a little bit odd, but in principle 0.7 seconds, 0.8 seconds, and so on. At some point the simulation should start turning. I think in 1 second it should start turning or not. Yeah. It starts slowly, but never mind. So you have the when you go up here to that part, next to home you have view. And this is very important. Next to view you have here the current time. You can see that also here. 1.08 seconds. And you can just scroll through or select a different state here. And this is more or less the thing that is saved. So if you click on start, here, not on simulation, but on play, those frames are loaded on the system. And you can restart the simulation and change the simulation at any point. And this is the second mistake that a lot of people make. They say, okay, I want to start earlier with the rotation or I want to change anything. They do not look where you are working in, because you're actually working at that time step. You can change anything here, right now, and resume the simulation. For example, I can change the segment in its angle. For example, change the segment here, so that it's nice. And then resume that the material stream increases first. A little bit more particles than before. So you can change at any point. And that's important because lots of simulations do not allow that. So if you make anything, let's say a feeder on a screen, and you start feeding the material and say, okay, now it's enough, you can just click on pause, go to the generation rate here, and just set that to 0 or just delete it, and now save it. And you click on simulate again, it just stops generating. So you do not need to overall start again, and again when you want to restart it again, let's say leave it a little, and you want to add, let's say at 8.5 seconds restart it again click on pause, design, particle generation, and again activate it. Let's see what's happening, again the particles are coming. So you can always pause, resume, and change things in between. If we now click on pause the simulation again and see back in time what happened, we can see that at first the particles were coming, then there are a little bit more particles, and suddenly no stream, and again a stream. So everything is saved. Where? Again here in this folder. Every second, everything that we can see here is saved here up to 8.8. So 8.8 is actually that file here. It is 6 megabytes, and all that is the simulation. So if I switch to second 6, that file is loaded. So if you have very large files with a few hundred megabytes, it's a bit of a bottleneck because it needs to load the big files in your visualization. So that much to the structure per se. You can change anything anytime you want, and if you want to restart everything differently from the beginning, don't forget to get back to 0. Because you're always working in the step that you're actually looking at. So far. Now we have the simulation, that is one part. So we have modeling, means design of the system. Second part, simulation. Again with the tutorial for now. And the last part would be analysis. So we want to have something visualized in our system. This is that one here. And here you can change the view so that that indicates something. For example, particles, the most common view would be particles coloring. I want to see the velocity of my particles. I want to see how fast they are. And now the color indicates the particle velocity. You need to go to analysis, particles, of course, coloring, and switch on for velocity. And don't forget to click on update. So you have between 0 and 8 seconds. So you have a good visualization of the color. If you only go for 8 to, let's say, 5, you can see that some are gray out. So those are beyond that range. And of course, that works also during the simulation. So if you start the simulation from the beginning, you are coloring through the whole video, so to say. This is the first thing. So analysis of velocity or energy or whatever you want in here. If you want to have the streamlines, where are the particles going, you can do a very good thing here. You can change the behavior from solid to vector, and you see some arrows in different sizes where the particles are flowing. So the arrows indicate the particle stream. In your case, probably a bit bigger, a bit smaller. Who is bigger arrows than me? Smaller? So you can change that here from solid to point view, okay, to inside of the system, or to vector view. That's good for analysis where the particles are actually going in the system. Good so far?
So yes, while I'm running the simulation.
What error? Working directly.
Wanna come here? Mine is working. Okay.
What was it that? Working directly. Yes. So you need a working directory where the files are actually stored. It's actually set. So it said working directory not set in the arrows. The first one was the working directory not set. Everything else was okay. Good, so it's working also at yours. So the VC++ did some good job. So who installed the VC file from Moodle? Just curious. Working? Not working yet? Not installed yet?
Installed, but it's not working.
Okay, we will, please afterwards we will take a look here what's happening. But should be working?
Yeah.
Working?
Yeah.
Not yet, I
Not yet?
haven't checked
Working?
it.
Who installed it already and it's not working? You're finished installing? Yes, but I think you have a different error. And the other ones all installed it and it's working so far. Seems good, at least on this laptop. Okay. So, simulation is working. Everyone who is now a working simulation without the program crashing should be principally possible to set up any simulation because it's not crashing per se. Good. So now there was a short overview from design to simulation to analysis. Now you know this is a bigger simulation, how something like a simulation can look like. Probably something like that can be your idea in the end, what you're working on. And also you can use snippets. So you can use something from the install folder, something from the tutorials. You can use that, build on that, export something, import something. But let's probably, now we have simulation of a complex system done that should be principally able to work. Now we figured out on which computers it was not working. Now we know that there were some issues, we resolved them. Probably let's switch back from that complex tube. It's only it's a little bit confusing for now. Let's get back probably to a blank system, new one, and open again our first test simulation. If you still have them, otherwise please just make a new one, or with your colleague, or follow. So we have our plane simulation with two planes, one on top, one on bottom. And principally the other ones are the same with a little bit more of them. But the basics are the same. So we have the particles in there already, with some of them generated as far as I know. Okay, yes. Here we go. And I wanted to stop here on purpose, because when we come back to our simulation, so forget the chute and the segment and stuff, so that should be your more or less status quo, right? Like working? Yeah, particles are coming out of the plane? Yes, good. Okay, so we have that the particles are coming out. And they should actually fully fall through the lower plane, right? They should fall through here. Why? What's happening? We define the particles, we define the plane, we define that they're falling out there, but why are they so strange? No collisions defined yet. Right. We said we need a Hertz-Milton contact model or something similar, so that the particles know that they actually contact each other. So we go to interactions. Oh, yes, there is something missing. Rock has no interaction, and rock-steel has also no interaction. Nothing defined here. One minor thing here. I just said that. I changed something, and I changed it in the current time step. Not a good idea, right? Because I'm at 0.4 seconds. I actually need to go back to the very beginning and define it here. So, from the very start, at second 0, here also, second 0, I need to define that there should be a contact between rock and steel. I change material A rock, material B steel, or vice versa, doesn't matter. And I said, which contact model, please don't look into that, just select the default one. There are lots of them, as you can see, predefined, and you can change any of them in detail, but just let's add the default contact model, dry Hertz-Milton no-slip contact. So we say, contact between rock and steel, defined. No slave model, no stickiness, no cohesive behavior, just dry material rock to steel. We double click it, and we have some details to fill in. We have material A and B steel. A lot of stuff to go into, but as you remember, what this might be, restitution. You remember? Particle falling from a certain height, jumping back. Let's give that 0.2, for example. So I want to have that something like that. A little bit damping, not too much, not too less. Let's start. Something between 0 and 1. 0 would mean, and 1 would mean, okay? So it's the restitution that jump back of the particles. And we have some friction parameters, also between 0 and 1. And that should actually be calibrated. But we start with some values that I know. 0.3 works quite well, and rolling friction a little bit less. So static should always be a little more than dynamic. It also says that to you if you started and it did not do so. So let's start with some values. And again, save. And now, if we go to simulation back again, and start, particles should fall out of the ceiling at some point at least. Yes, they are here. And check, I mean, it's very slow at my computer because I have a very small time step, only 2%. We'll come back to that. So, does it work? Point. Yes, we have contact, a little bit of jump back, not that much. And the next particles are coming. Let's see from the side what's happening.
They won't collide.
Yes, they won't collide. Why?
Because we didn't define the interactions between
Same
particles.
thing as before. Absolutely right. So we can go back, interactions, and we define rock. At rock. Similar as before, but I want to have stone to stone, even with a little bit more damping, like 0.1 or even below, something like really, let's say, like rocks. Rocks do not do like that, like steel balls. Rock are more, let's say, damping. 0.1 and static friction, I choose just the same, so I have starting values. Again, save, and I start the simulation. And before I start now, it's really slow. It's not really what I want. You can see here 2.64%. doesn't say that much to you, but probably you remember also from the lecture, there was a time step that was critical, the Rayleigh time step. And it was like this shock wave going through a solid particle. If you have a very rigid particle, a very small particle, you need a small time step. The program automatically computes in the background a time step that is suitable. And 20% of that time step is a good value to start with. So I changed my time step that here is about 20%. 26, 30 might be okay, but it's probably not stable anymore. I will show you in a minute what that means. 26 should work. I want to simulate not 1 second, but 5 seconds in total. Again, I save, and I start. And it should be much faster. Yes, particles are coming out. And we have contacts. Perfect, looks good. So we are already at second 1. Particles that leave the system are deleted, you can see that here. And the particles are more or less thrown here on the plane. Now we can pause. I can also change the time step at any time I want. I already said that, right? I can change anything at any second. I will stop now. And now I will show you what it means if the time step is critical, right? This would be a supercritical simulation. Time step is much too big. If anything like that occurs on your system, your time step is too big. You go back where instability occurred. You see, at first it was stable, and at some point it went unstable, where I changed the time step. That is a stable time step. So as long as the simulation stays like that, it's okay. As soon as the particles explode, poof, everything goes apart. Simulation is super stable. Good. Now another thing that I did not want it. I said I do not want these perfectly regular patterns to occur. Probably go to design, particle generation, that's where we left before. And here is regular. Let's change that to Poisson, which means randomly distributed, and I want a little bit denser generation, so more particles after another, so not every 0.2 seconds, probably every 0.05 seconds, or whatever. Save, so the insert interval is denser, so particles are not entering like pop, 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 raindrops much faster. Save, and let's see what's the difference. Yeah. A denser particle stream, more particles, and we're shooting our plane here. Cool. Everyone so far with me? Not.
No.
Okay, but we will rebuild it anyway once more, but with a box.
Repeat from the collision
Sorry.
from the beginning.
Yeah. Ah, you already get it. Good. We will do it again with the cylinder now. We'll do it again, and everything that you did not get up, you can follow now. Okay. So now we have tried the first thing, the first idea, the first concept of a plane in mid-space pouring a heap on it. Now we want to fill something. We want to fill, and that's the first thing for our lab report. Probably you can also consider that as your example for the report. You feel free for whatever you want. Now you get an idea what is the effort, and it's a lot, of course. But if you're into it, it's quite, let's say, straightforward. Now let's start with our second idea. First one, plane filling with particles. Now we want to have a cylinder on a plane. We want to fill the cylinder with particles, and then lift the cylinder so we get a heap. What's that test called? Lifting cylinder. Exactly. Perfect. You ready for the exam? No. Let's start again from the beginning. New simulation. So everyone that didn't catch up here and there can follow now from the beginning, right? Very grüne Wiese. Green lawn. Yeah, if anything is missing now, contact models or particle generation different or anything like that, we will address it again here. We will do the whole thing, but not pouring on the plane, but pouring into a cylinder, filling the cylinder, and then lifting it. So now not on the plane, but into a cylinder. And everything that you didn't get, like contact modeling, we'll do that again. Now, so, new setup, Blanco. What was the first thing that I said we should define?
The material.
Right, very good, material. First material, we call it bulk. Bulk material. And the second one, we call it steel or rubber, or let's call it steel. And the second one, we call it plexi, like our cylinder of the, the lifting cylinder. Good, so we have three materials, bulk, steel, and plexi. Again, double click, bulk, again 2500, good value to start with. Shear modulus, let's stick with 10, it's also a good value, very fast. The lower the faster, by the way. I can show you in a minute. And we just put a steel, again 7850, doesn't make a difference because it's rigid anyway. Shear modulus, again 10, Poisson ratio 3. And last material, plexi, I don't know, 5000 probably. It's rigid anyway. Shear modulus, again 10, and Poisson ratio 3. So we have more or less three very similar materials. Safe. First thing, safe. In our system as before, we call that lifting cylinder test. Safe. Good. Second thing, now we define materials. What now? Yeah. What should we proceed with? Parts or particles, or what should we do?
Particles.
Let's go to the particles. Okay. Again, maybe something different now. Probably could be. What should we choose?
Multisphere.
Could be multisphere, but then we define several spheres. Probably stick with torus. Torus, you like torus? Okay. Go there. Torus.
Torus? Okay.
Oh, I call that torus. Doesn't matter. Torus. Okay. Torus, I need to define an outer diameter 5 centimeter, and the radius of the torus itself 0.01. Let's see, I like that a little bit bigger. Yeah. You like that, a donut? Yeah, looks good, right? Cool. Safe. Now we have our donut. Then we define our parts because we want to fill something, right? And therefore we need at first a plane. It's pre-selected. Okay, let's say plane. We call that round. Round. Okay? Round. Double click it. Looks not too bad. Let's stick with that. Then we need a cylinder, obviously. We call that a cylinder. We double click it. And go to position. Here we can define the size of the cylinder. Are you with me so far?
Yeah.
No, too fast. Too fast.
Okay, I defined the ground and didn't change anything, and I defined the cylinder. Okay. You can choose whatever particle you like. I decided to choose a torus because someone of your colleagues said so. Okay, I defined the torus, named that torus, okay, and double click here. Probably add to like that. Maybe that helps, I don't know. That's a good idea. Where can I change the, where do I magnify? I don't know. Does it make sense? Should I turn up the size a little? Or is it okay? It's perfect. Does it work? Okay. So I defined that parameters for the torus. So 0.05 for the outer diameter, 0.02 for inner diameter. Ooh, and I forgot something very important. What?
Define the material. Define the material for the particle.
Yes. It should be made out of bulk instead of plexi. Good. That's a very common mistake to be fair. After that, I directly switch to parts. I define the ground as a plane. Plane, we put the ground. And then I define a cylinder and call that one cylinder. Very clear. But the cylinder is not defined yet in its size. So we have the ground with 1 meter times 1 meter, that is default, but you can't see the cylinder because when you go to position, the cylinder has no radius and no height yet. So if I increase that a little, I can already see it a little. It's too big. Let's say, I don't know, 25 centimeters would be good, I guess. I think it's the size of the thing we have in the lab. 25 centimeters in diameter. And half a meter in height is also cool.
125.
Yeah, that's the radius. So it's 250 diameter. Yeah. Yeah. Okay. One problem now. The cylinder is not on the ground. We need to lift it a little. Exactly a quarter of a meter. So that it's on the ground. Looks good so far. And we need to remove the bottom. So now there is a bottom and the top. We can remove the top. And we remove the bottom, so then it's a hollow cylinder. Good, right? So far so good?
Yeah.
Good. Safe. Okay. Victoria? That's a plane. You need to go to parts. Delete the cylinder because it's a plane. And select cylinder, yes, select it. And now we call it cylinder or cylinder or whatever. And now double click it. And go to position. Now it should be there. No worries. If anything occurs, just interrupt me so we can catch up. Or if you say stop here or go back, please do that because I don't know the speed if you don't interrupt me. Okay. But you have the cylinder now on the plane, sitting like that. If we want to pour particles in, what do we need?
A particle generator.
Plane, a generator plane. Right here, plane. We call it again, gen, plane or whatever, a generator or something. But it needs to be a plane. Yeah? Plane. Enter. So we have a gen plane. Yep. Good. Go to position of this generator plane, it's already red. And we lift it up. That's the first thing, because we want to have it above the actual cylinder. Probably not that much above. Oh, that's too low. A little bit, something like that. So 5 centimeters off the cylinder. So 0.05. It's much too big. Most of the particles would go on the sides. So we'll make that a bit smaller. What would work? Yeah. Probably something like that should work, hopefully. Good. So we have that. Last thing that we need to check, if we go here to our ground, what do we see here? It's made out of plexi. Yeah, should be steel.
So Eric, can you change the generator with another shape?
Yes, with a workaround, but let's stick with a rectangle.
Okay.
You can change that. I will also show you something different in a minute, but let's start with filling it up with a plane and then try to fill it at once. Not with a rain, but with an instant one-time filling. You do that as well.
Yeah, because I thought of some real operations.
You can do that.
Okay.
You can choose a different. You can do that if you want. You can change the plane and instead use a cylinder for a generator plane. And if we put I will just do it because it was so set position a bit higher, like here. Yep. And you can use that as well. You say, okay, the 8 a little bit, something like that. But you need to define that this cylinder is not collision detected. Okay. So you need to turn that off, and then it can be used as a generator plane as well. You can also say that it is not shown, but we can try it with that if you want. I hope this works for donuts. I'm not quite sure yet. Should actually, but yeah, that's right. It's also something we can do. I will just set it to the same diameter so that it more or less fits the opening here, and then the donut should come out here on the bottom. If the donuts are not too big, I hope. I don't know which size to make, but we will see it in a minute. There can't happen that much, because if something's not working, you just try to change it. Nothing's wrong. I will try with that. You can try with the classical planes as well. No difference, okay? No, just stick with the plane so far. I will recommend it. Probably I will even change the opacity a little, let's say to 50%, so I can see inside of the, something like that. Good. So I can see inside of the system. Here you can change the transparency of the system. You found that probably out on yourself. You can say outline view and transparency. Okay, we have the generator, we have the parts. I wanted to check the parts for material. The ground is made out of plexi, that's not right. Ground should be made out of steel. The cylinder should be made out of plexi. And the topper thing out of plexi but collision off. That's my current setup. So now, we need to define the particle generation. And here, that's what I wanted to address before. You can use generator, classical one, coming out from the generator cylinder here. That's the classical method, but you can also use a filling. So you can fill a whole volume with particles at once. Not layer by layer, but a whole volume. Now let's start with the generator and say I want to make a gen from, and that's important, from the generator plane above or the generator cylinder above. If I double click it, I see it again. Now that should be red. The thing above your cylinder should be red. You so far with me? Either your plane or my cylinder should be red. Yeah, torus should be coming out there. Wasn't so bad before. Let's start with velocity. 2 meters is okay. Downwards. Start time and stop time, very important. Most of the people forget that. And that should be it. One major thing, our domain. The domain, if you look at that, not working with that because our particles are generated here and would be deleted instantly. In the last simulation we didn't address it because we stick inside of our domain. Now we need to adjust that a little. So here you can change the size of your domain. And a good start point would be automatically update and try to fit everything around the particle, the boxes, except the one that is set to no collision. So you need to adjust that a little in its height, a little bit higher, something like that, and you're good, more or less. So doesn't look so bad, right? Everything is inside, looks good so far. What is the cell size? So here, you can see that this is the cell size. And I also do not want to exaggerate that because this is a science for itself, the appropriate setting of the cell size. A good rule over the thumb is to set the cell size above this, in the area of the size of your smaller particles, So if you have a very small cell size, for example, like that, much more cells. More to compute. If it's bigger, something like that, it's okay. Not that much cells, about 1,000. That's okay. But the computation of the contacts might be a little bit more complex. So there is a trade-off in either direction. I would stick with a value around the size of your particles, and I remember we have an outer diameter of 0.02, right? Something like that, or 5. So it's not that bad in that area. Probably a little bit smaller, something like that. A little bit more, because 1,000 is nothing. 1,500 still not that much. Let's see. But can we bring it off again? This one is important. So that all of our parts are inside of the domain. Otherwise, it won't work. Most likely. Save again. Go to simulation, and let's see if it's ready for run. Okay, now it's showing me the this should be set default, yes. Let's see. Okay, there is something, not an error, doesn't throw me an error, but no particles are coming in my system. Are in your system particles coming in the simulation?
Yeah.
No. From your plane? I will try changing it to a plane, okay?
Yeah.
I don't know if torus particles work with that form of indent. It's possible.
Pero están atravesando acá, no puse la colisión.
Because I do not often work with a generator plane made out of cylinder. Let's see if that is the issue. No. I will change to the plane. Who has a plane? Is working with a plane?
Yeah.
Then that's probably the issue. Is the size okay? I will just reach it.
No, I think the torus should be
The
smaller.
donuts are, yeah.
Should be smaller?
Yeah.
They're quite big, right? Yeah, I thought so. I just tried myself.
Oops.
Let's see. Is that too big? Yeah, it's too big.
Como dije, es más chiquita.
Let's see. Not regular, but horizontal would definitely be a good idea. And let's see. Yeah, they're quite big and no collisions defined yet, but they're too big, definitely. Yeah. Make them a little bit smaller. Actually, it should be possible to change them during the simulation so we can see how big they are. Go to design, particles. 2 and maybe. That doesn't look too bad. 2 and 1 to 5, let's see. Okay. Yeah, that looks better. So it was, what was the size? Don't forget to go to 0. What was the size now? 2 and 1 to 5, right? Okay, I changed that to that. I leave that open. Should work with that. And at second 0, because otherwise it won't work. Okay. Everyone so far?
It's not working.
Not working?
Yeah.
The program or?
There's no particles still.
Okay, who has some troubles?
¿Ves que lo hice?
Yeah.
Ah, me faltó guardar los planos.
Yeah, we'll change it to something else. We will change the generation anyway. No dots?
Mate.
Yeah, we changed that as well. Yeah, we will remove that. Okay. So now, most of you have seen there are some donuts, but probably now we will try a different method. We will try filling a volume at once. Okay, so we try, instead of filling by pouring down the donuts, which is not a bad idea for donuts, we will try to do that with instantly filling. So we go back to 0, and instead of using that plane here, we can delete that plane. Delete the generator plane. Delete. Yes. Then it should look something like that. So we have a plane, an empty cylinder, hollow cylinder, and now we go to particle generation. Instead of selecting generator coming out of a plane, we select filling. So we want to fill something, and in that we call that fill 1, whatever, fill. Double click on fill, and there are some things to set. What do we want to fill? We want to fill torus into a box. Primitives, yes, we want to fill a sphere with a radius of, a cylinder with a radius of a certain size and a height of a certain size. Now there is something defined here, a volume, you can see that already, and that volume will be filled with particles. You can already try that if you click on add. And you see that volume is more or less filled with donuts. We don't want to fill that regularly, we want to fill that in a Poisson manner. So randomly distributed donuts inside of this green filling. You can add and delete them if you want. Please don't click on add several times because the donuts will overlap. They will add it and add it and add it, but they will not care for overlaps. So just please click once, add, and you see that there are some donuts in there. So far?
Yeah, yeah.
Fill it and select the cylinder, Poisson, and the direction of the donut should be in the Z direction, so it is upright. And you can change the position a little. Definitely we want to go up, like that. And most likely there are not enough donuts in this filling. So I can add that, but yeah, this is not enough. I would say what we will do is we want to increase that volume that we want to fill, about triple the amount of our cylinder. So like that. That's too much. Like that. Like that. So, and fill that volume up with donuts. It's working now. But as soon as I click on simulate, all the donuts up there will be deleted. So I need to also change my domain. So that the donuts are inside the domain. So I have a tower of donuts ready to fall into my cylinder. I have full control of how many donuts there are. It's a little bit more convenient in lots of cases when filling something. Instead of pouring something in, you can just define a volume, for example a sphere, or a box, or a cylinder, and fill them. You can also, what's also interesting, you can move that. So if you want to have several of them, probably here a few, there a few, you can change that anywhere you want. I mean, it doesn't make sense here, but if you want to fill 3 side-by-side cylinders, you can just fill, and let them settle in. Okay. So I have my donuts here, and when I go to simulation now, they should. What should they do? Let's see if anything happens. Nothing happens. Why? Very, very, very important thing that we have here on Earth, different to the moon. Gravity. We didn't define any gravity yet. Design. That's also a very common mistake a lot of people don't think of. Loads, there is no gravity set. On loads, there is a bar that means gravity, and you need to have gravity in the Z direction, minus Z, minus 9.8 or whatever. Save. And now, let's try it again. Again, it times at 0. Start. Yes, they're accelerating down. No contacts yet, of course, we didn't define any, and the particles that are outside of the domain are removed. Pause. Back again. So far, gravity, filling, good. Who's with me? Good. At least one. Now it's actually learning by doing, and if you do, I will show you also. I mean, it's 12 now, but I will show you in the end some of the tutorials where you can click through. There is also a PDF with some descriptions, easy to follow. But most of the stuff is learning by doing, and that's also why I'm not a big fan of recordings, because anyway we have the PDF, so I don't need to record a lot of stuff because the PDFs are there. But so I can more or less go up there and through them and see where you're missing some points. Good. Donuts. Who has the donuts already on his screen visible? Good, good, good. That's good, yeah. Filling?
Set the filling?
Yeah.
Ah, bah. Holy macaroni. Yeah, okay. Yeah, you're trying out a little on your own. Yeah, no worries. If you want to try out here and there, add some contact models already, no worries.
I activated the gravity, but
Gravity is very important because otherwise the particles won't fall down. In the last test we didn't do that because we shot the particles down anyway. But without gravity there won't be a heat form in the end.
Yeah, they
Good.
do not
So we
know.
have the gravity. Last thing, same as before, interactions. So same thing. Materials, parts, particles and particle generation. And in the end, interactions is also important. And don't forget the domain if you have troubles with your size of the system. The domain should be around the system. I will highlight that also in the end. So, let's go to interactions. Here, we need interaction between bulk and steel, and between bulk and bulk, of course. We need between bulk and plexi. That's it, right? That's it. Everything else is cool so far. Bulk and steel is the first contact to the floor. Restitution of 0. Donuts are quite soft, right? 0.1. Static friction higher, let's say 0.5, 0.4. Bulk, I would say, ooh, this is even more soft, 0.01. Just put some values here so that I can proceed. And plexi is a little bit, I would say, here again with steel. And 2. Okay, I put some values here so that I can proceed. Okay, I have 14% of my Rayleigh time stage here now. I can increase that a little. Okay, not so bad, about 30%. It's quite high, but hopefully it will be stable. Before I click on simulation, I want to show you what the shear modulus is all about. Why we set that with 5 instead of 10. Now remember, we have here 30%, around 30% of our critical time step. If I change my shear modulus of my bulk from 10 to 50, for example, it goes up to 66%. So decreasing the shear modulus gives me a much more efficient simulation. When I decrease the shear modulus to 10, this goes down to 30%. Okay, materials, bulk, I changed that here, 50. And only for one material, not for the three materials. Yes? So, save, 30% and hopefully safe, let's see if it works. And the donuts are falling in my box. And at some point they somehow get deleted. I don't know. Let's see if I can find everything right. Parts, steel, right, plexi, bulk. Why is ground bulk? Ground should be made out of steel, plexi. Okay. The particles are made out of bulk. This should work as well. So probably this is too much. Let's see if it's. Let's see now. Probably 30 was too much. Happening, let's see. Yeah, looks better. So 30% was critical, everything went unstable and the donuts fell out of the system. So looks good. Good, not so bad, right? Oh, unstable again. Yeah, you see that? At some point it suddenly gets unstable. And that's probably also one thing. With spheres, the critical time step is working quite well. As soon as you leave spheres towards donuts, totals, like objects, boxes, cylinders, capsules, something like that, critical time step gets a big problem. So this is too high, we'll go down even more. And this is actually have you received the project studies yet? No. Okay. You received them? The Austrians know what I'm talking about. So there are some project studies here that you need to do, and I propose one. A very, let's say, simple one where you do not need the lab too much, but the computer. So I would propose anyone taking that project study should have a computer with the software running that I just gave to you. So you should have the running system, and the idea is just to change different particle sizes. So change to donuts. So start with spheres. Find out the critical time step. So okay, let's draw the sphere on the bottom and stable. Everything good. Increase the time step a little. Unstable, catastrophic. So make a Newton's approximation and find the stable time step. So I decreased it, and 0.05 works like charm. So particles are in there, they're moving a little, but that's it. If I increase the time step to a certain point, let's see what's happening. I increase it to 0.01 and I start, and the thing suddenly starts at some point. Okay, that seems kind of critical on the limit. Let's increase it even more. And boom, unstable. Going back. And again, so I find out which time step leads to an explosion of the system, right? And I want to do that for different particles, so for cones, for capsules, for stones, for different shapes of particles, and find for the same size of the particle in volume, for example, in volume, which time step is critical at which. So I have a table, which time step is critical for which shape. That is a very, let's say, general project study in doing with that system. So we filled the cylinder. Everyone so far, we filled the cylinder with donuts, and it's more or less full. Nicht? Oh no. So we have some cylinders filled.
Es no para. Nine es la respuesta. Una pregunta así. Nine. Entonces tengo que meter. Darle una oración. Yo tengo una pregunta. ¿Fuiste a bailar ya? ¿Sí o no? Nine. En cambio, si vos querés decir no fui a bailar, metes el mismo en la oración.
Ah, ok. Como para respuesta de sí o no.
Claro.
¿Y el dios es hay?
Ya.
Ya.
Yo. Not enough space, but I will upload it on YouTube. You don't have enough space to copy the video, but I'm going to upload it.
Aber da oben, da soll es, wenn die Gravity eingeschränkt ist, in 10 soll es so.
¿Vas a ir a comer? ¿Dónde vas a ir a comer? ¿A qué hora lo dirán?
Pero como el ligerito.
Ah, sí. Viste que es muy
The cylinder. Translational, yes, I don't want to rotate it, I just want to lift it. So translation, and I want to name that lifting. So, I have to lift it. What are the details? I want to lift it in the Z direction with 1 meter per second for 1 second, which means 1 meter. Instantaneously, so no ramp or something, but just starting to lift. And let's see if that works out. Start. Yes. And our cylinder is lifted, slowly but steady. And you should see at some point, and hopefully, it depends on the friction, that some particles are falling out of it. I mean, this is slow motion, right? Don't forget that. A little bit interlocking. Doesn't look so bad. Don't forget, this is slow motion. We are just at 0.7 seconds. And the second thing you can already see is that particles are also sticking on the wall because the friction on the wall is quite high. So probably changing the friction on the wall a little bit to lower values would help. Yeah. And probably the velocity is also quite high. 1 meter per second is like that. So, yeah. I think at the lab we are running with 6 centimeters or so per second. So, yeah, and that's it. it. And after then, 1 second, simulation is over. If I can see now, okay, I want to have it a little bit longer, I can even extend that. Say it should run further than 1 second. And in the end, I got something like a heat.
Can you reset the simulation with the current setup? Or do you usually build everything and then start the simulation? Because now
Lo metí en movimiento para levantar el cilindro.
Yes, that's a good point. Comes to that.
Uso movement en diseño.
So, the question was, if I change something that's 0.5 seconds, hence that's 0.5, for example, lifting of the cylinder, and I go back to second 0, the lifting is not there, right? Yes, and that's the case. So I typically, when I know I want to lift the cylinder later on, I define from the beginning, so here, the movement. And if you can see here, no movement there, right? Because it's not defined yet. And if I proceed on, at some point, 0.5 exactly, there is the cylinder lifting suddenly appearing. You can see that? So it's not there yet. What I do is I define almost everything at the beginning. I define a lifting here and say the lifting should start at 0.5 and end at 1.5. That's the idea. So I define more or less everything at the beginning. If you want to figure out if something works, also in your case, if you want to change something later on, you more or less, most likely, will work on one setup. And you can change here and there and there. No worries. It's a, let's say, work in progress. It's quick and dirty. If you want to do it, let's say, academically correct, the master's thesis, for example, this architect, for example, is currently working with me on the bucket elevator. He's looking at the bucket elevator made out of material A versus a bucket elevator made out of material B, and pours material in, exactly the same material in both systems, and she turns it over a head pulley, so the buckets this level, right? They unload the material. And she's analyzing which material, A or B, performs a little bit better. More or less. That's the idea. And she's doing it with that. So she defines more or less everything in the beginning. The movement of the bucket, the pouring of the material at the beginning. So I would recommend define as much as you can at the beginning. In our case, we didn't know when we wanted to start the lifting, right? Was it at 0.5, 1 or 2 seconds? I don't know when the thing would be filled. So I said, okay, let's start with the simulation. And click on pause at 0.5. Around was a good time because the particles settled. They were quite fit. And at that point, I said, let's start with the lifting. And in the end, it looks like that. Not so bad. And the question could be, how long should we simulate? And a good indicator would be, you can do an analysis during your simulation for the particles regarding velocity, just as we did. And take a look, for example, between 0 and 2 seconds, and take a look if most of the particles settle. For example, that donut seems to roll away. So if the particles settle and there are not that much colorful donuts, more or less all blue, then you're probably good to stop the simulation because the particles settle. Before that, there is movement in the particles. You can't see it with the naked eye, but with the analysis, you can see that some of the particles are still moving. And after a while, we're now almost at 1.5 seconds, a lot of the particles tend to stop. Not too bad. So, looking at that with the velocity view, we look like that. Yes. And now it was made with donuts. You can do that with different material setups as well, also with mixtures, and it will give you that. We're done anyway. So yes, that was donuts. And now would be the question, if you want to switch the material, you can just do that, go back, design, add another particle type, and that's it. So we have now movement already in there, different contacts, gravity, all those major things. And I would say if you make a snipping thing here, say, yeah, the design, like here, I would start with the materials, define my materials that I already have, then I would actually recommend going to the parts so that you can already see something like a cylinder, like the plane on bottom. Then go to the particles. Define the shapes of the particles. Probably also the particle generation. You definitely need that. Interactions is very important. It's right after the particles. So how do the particles interact with the surroundings? And don't forget the domain. Everything else is probably not required.
Okay.
Optional things
Oh, no.
that you most likely will need to use is movement. Probably also an interesting thing. And mix. Where is it here? Particle mix. That would be also something you probably would look into. Everything else, leave out, because you don't need them right now. It's too complex, much too much. At last, I want to give you an idea of what particle mix is, and then we make a short wrap up so that you can also do that again easier. That's why I want to say it's easier here explaining rather than you trying it out on your own, I guess. So we can stop now.
Can you put the screenshot again, please?
Yes.
Snipping.
The other things, this is multi-body dynamics, that one here. I'm sorry. I don't know if you can see that, but on the bottom, on the top, this 6 DOF and stuff, this is multi-body dynamics. You can see fluids here, you don't need that. Finite elements, you don't need that. Heat transfer, where you don't need. Oh, last, almost forgot, don't forget gravity, right? That's also. I mean, it's complete, but don't forget.
And load.
Yeah, and in the end, it's not rocket science in each of those tabs, but each tab must be filled. If there is no material defined, you can't proceed. If there are no particles defined, you can't proceed. That's it. And before we start, before we stop, I want to show you what you can do and where you can find snippet and so on. Going back to the install folder. Backup 3D, install folder. There are some other files rather than those two. There are documents, examples, and tutorials. You already looked into the tutorials, what that is about, and probably that's a good start. If you want to, the easiest thing is probably the transfer tube. The segment is also not that complex. Just start the segment. There is a PDF file. If you open the PDF file, you can see what this file is about. So it's a transfer tube, looks like that, and it's a step-by-step explanation what to do to achieve exactly this simulation. Exactly as we did. When you start with, for example, here at the beginning, general. We defined the material with the name granular, 3,500 kilograms per second, 5 megapascal shear modulus, exactly as we did. Second material, steel, exactly as we did. 7860, 10 megapascal, 0.3. You remember that, right? Then he said interactions. Restitution 0.1, as we did. 0.65, higher, but the same as we did. He defined some, let's see. What did he define this? Well, he defined parts and properties. Same as we did, but not with the pre-existing ones, he imported ones. And that's probably the last thing also in terms of complexity. If you have more complex things rather than planes, cylinders and boxes, you can just use 3D CAD files, for example, STL file. That's an STL file. It's very simply opened with Windows. You can open that. That's the segment from a CAD program, and you can import that directly in the program here. When you go to design parts, mesh, then it switches to import, and you can choose the file you want to import. For example, I just import something, anything from my side, Chalk Russia, Chalk Russia should be a CAD file anywhere here, yes, STL, that one. I want to import that in meter, and then you have the Chalk for Chalk Russia in your system. It's not a big system because it's for VR analysis, takes a while, it's made out of small triangles. Now you can see there is a Chalk Russia's jaw in here. And if you look here for the wireframe, for example, it's made out of a lot of triangles, mesh. I created that in the CAD file, can be used in the system. Yep, that's it.
Professor Eric, please remember to create this this file where we can vote for the dates.
What?
To create this quotation where you put your dates where you're available,
Good point, yeah.
and we can vote which are suitable for us.
Absolutely good point, yeah.
And you put it in Moodle.
And I also will write it on mail. Good. And in that file, there is this PDF, and next to those files, that's because is those EMP file you can import. And aside from the tutorials with the PDF step-by-step introduction, there are also examples in documents. Documents is one thing. I mean, it's very comprehensive. The user guide has 360 pages, but if you want to find out something about the interaction model, something is all written here. No need to worry, you don't need that. What you might need, what would be a good thing, is the examples. Because in the examples, there are lots of details to contact modes, to particle shapes. For example, particle shapes. You say, I want donuts, or I want, I don't know, capsules. You can go to the particle shapes. And for every particle shape available in the system, there is not only an example, but also a video. So if you want to see how a capsule looks like, you can see a video with capsule. Let's see if it opens. Yes, it opens. So capsule-like particles, not spherical ones, but capsule-like in the pharmaceutical industry, are poured into a box. And this example is in this EMP file. So this EMP file, you can import that. Right, give an example here. If you say file, import keyboard file, and use that capsule input file, you get exactly that input file. If you start the simulation now, it's similar as the tutorials, gives you this exact video that you've just seen, but in your simulation. So you can use every example. There are lots of them. This is one. Capsules, there is something on, I don't know. For example, fluids, you addressed that. A Yanno-Ray. That example is in the system. There is a water, for example, water simulation with particles. A Yanno-Ray. Or the puck, I think there is the hockey puck. Yes, there is a hockey puck dripping into a fluid. So it's a particle falling into a particle-made liquid. There are all those examples, all in those EMP files. Just import those EMP files, copy it, I don't know, multiple dynamics, for example, loads, fields, everything in there. Stick with the simple ones, I would say. For example, movements. Cyclic movement, I don't know what that is. Oh, screen, cool. Probably that's something for you. Exactly that thing. Maybe that could be a good snippet for your work. If you want to say, okay, I want to combine complex shaped particles, carrots for example, screening carrots from bird particles, that could be a good thing. So you combine the screen here, exactly that screen. Copy that to your working directory, file, view, start from view, file, import, keyboard file. Second, what's the name of the thing? Import it, you got that, and you can already start the simulation. Save, of course. Select it. Start. And it should work. And you have the simulation. There are two particles coming on, the larger ones here, the smaller ones here, and you just change the type of the particles. You already have seen how a donut can be made. Cool. If you say, okay, I want to simulate a carrot with dirt, that probably means cohesive material behavior. Is there an example of that? That means contact modes, because contact means cohesive material behavior. Contact modes. Compressive, compressive, non-compressive, sticky, non-compressive, sticky. So sticky material, let's see how that looks like. So he defined a sticky material here, more or less brittle, probably too sticky. So you combine, all those examples are in there. Take a look, and then probably think, okay, what can I do? They don't need to be realistic or relevant examples, they should be achievable, right? I mean, doing a sack mill with slurries and stuff, anything, probably a little bit too much. But if you say, okay, I want to have a cool idea, I have a cool idea of a grid, or I want to compare different grid types, hexagonal versus classical ones, you can do that. Just an idea, moving something, pouring some particles in there, and it should be achievable on your system or on my system, not on a supercomputer. That's it. But have a look here, there are some cool videos, and they're easy to import and just click on start. Should work. But I think we're good for the day. We'll remember this, the thing because of the dates. The earliest thing I would say is tomorrow afternoon, before that is not possible for me. That will principally work. I will start with that, and then please just vote and you will find a suitable date. The important date I want to set, and that's the last thing I want to address from the administrator side, is the exam. Because for the exam, most of you should be here, hopefully everyone, except he or she is not well. But we need to find a date. So I want to propose, probably it makes sense, to do the exam next week, because next week on Wednesday, everyone should be here. You have seen the theory after all, because that's the only part that matters for the exam. You know everything about the physical particle stuff, lifting cylinder tests, bridges that are arches that are formed due to cohesiveness or to mechanical bridging. You know that stuff, right? Everything from the slides. Also a little bit, and yes, it will be twofold. First part, physical world. Second part, obviously, digital world. A little bit about the DM, time stepping, too large time step, things like that. So very on the basic, on the theory level, nothing about equations. I will be here, I will support you, I will look over your shoulder. Last year, the grades were pretty good. I think there was one free, what is free? I think it's C, right? There was one C grade, everyone else was A or B, so they were quite good, but to be fair, they were well prepared. You should be as well. So you have seen the theoretical stuff. I will propose doing the test on Wednesday next week, because everyone should be aware of that, should be there, and we will definitely respect everything regarding the dates. So this Friday, nothing, and next week we will find some dates. Okay? Anyone objects against next week, Wednesday? Okay, then I will write a mail reminding of that, and it's a written test here. So I would propose next week, Wednesday, right in the beginning, we will start with the test. Should take us